Okay, now we have gone through the fundamentals of designing the flocculation tank and repeat mixing. Now I want to talk about sedimentation tank design, which is again an important aspect. If you want to have, you form the floc, you make the floc bigger, agglomerate it, and then you want them to settle down. And then you have to give enough time for the water to settle down. That doesn't mean you can't just keep the water there forever. You have to keep it at a certain time that is sufficient enough for most of the floc to settle down. You can never get 100% removal. You will get, usually sedimentation tank is targeting about 70% sediment removal here, because they don't set, if they settle down, the smaller particles, they take quite long time, so it's not efficient for us to keep the water there for very long time. So usually the sedimentation tank is designed for 70% of sediment removal. The rest of the one is removed by another process called the filtration, which we will talk later, but the sediment removal is the one that we are going to consider here. Now, to consider this sediment removal, we have few definitions that I want you to understand before I talk about the design. The sediment means some particles have to settle down. If a particle is going to settle down very fast, you can imagine that means the particle settling velocity if a particle is going to settle down very fast, then you will see particles will be removed very fast too. Now, if I pump the water through a container very fast, then you will have less particles settle down. So you have a container, and then if you take the water out very fast, so if I pump the water through here and then the water comes through out here, and this one is going to go at Vs, that's the velocity of the particle. The water is moving at a particular velocity, let's say V0, and then it goes above the tank and then come out. If that is the case, if V0 is going to be higher than Vs, then it will take the particle with them, and then all the particle will be washed out. If V0 is equal to Vs, then some particle may be removed, or if V0 is less than Vs, definitely most of the particle will be removed. Now we will see this particular case later, how I want to, at the moment don't worry about this one. If V0 is less than, so Vs is greater than V0, and most of the particle will settle down before they come out of the tank. Now what is V0 here? We define this V0 as overflow rate. V0. That's why VO is written to mean overflow rate. Some people call this one as surface loading rate because the water is assumed to be flowing over the top of the tank. Surface loading rate. Now you might ask me, does the water always have to flow over the top, or does it have to, can the water come through in another place, and then can we design this particular situation? So now that is what I want to now go through and then explain to you how this one can be applied if it is a different situation. Rectangular tank. In this rectangular tank, let's say that has a width of W length of L, the height of H. And then let's imagine the water is flowing here. This is how most of the sedimentation tanks are. Either they are rectangular in shape or they are usually the circular in shape. I will explain in the rectangular shape first, and then we'll develop the equation, and then we can apply it anywhere we want. Now, if the flow rate is going to happen in Q, then we know the retention time, which we studied before. The retention time theta is given by the V, which is the volume, divided by Q. V is the volume of the tank, which is L, length, times the width times the height, divided by the flow rate Q. Therefore, Q is given by L times W times H divided by theta. So let's put a number there as number 1 for that particular equation. Now let's look at the flow rate, the surface area here. Surface area is W times L. Therefore, the overflow rate, which is V naught that we described, is the flow rate, which is Q the flow rate, how much water is going through this one, the flow rate divided by the surface area, which is the top surface area. That's what we considered in when we are considering that particular situation. So the flow rate is going to be LW times H divided by theta divided by surface area is W times L. That is this surface area here. When you divide it, you get H over theta. So you can imagine, you can look at here and then feel that V naught is a function, which is the overflow rate is function of height and the retention time, how long the water is staying. Now, how do we apply this in a situation where we have the water is moving? Let's say here a particle is entering in every depth. The particle is entering. If you want to have all the particle removed in this sedimentation tank, you can imagine the particle going in the top has a greater chance of escaping because the water is flowing this way. Greater chance of escaping, and then the topmost particle have to hit the bottom of the tank. The topmost particle has to hit the bottom of the tank. So when that happens, then this particle, because the particle will fall down vertically, water is flowing horizontally. So by the time the water reaches this point, this particle has to settle down this height. So you see this H here, that's the height. The time it takes for the particle to settle down at any given time, let's say it is only settling down, let's say we take another one here, and then this one only settle down only that much. If this much is the one that is settling down, that's only the particle is settling down that much. If the particle settle down completely to the bottom, the one that is entering in the top, going down to this one, then all particle will be removed completely. That means that is the time it is taking is theta for particle to travel from here to the water to travel from here to there. During that time, this particle has to drop height h. That means the particle velocity has, if the particle velocity is same as h over theta, that means v naught, then you get 100% removal of the particle. Here Vs, when I say Vs, this is a particle settling velocity. If the particle settles in the way that it can drop down to the total height of h within that given time of theta, so if they can completely drop the whole height within the time theta, then this particle will be 100% removed. If you have another situation, for example, the particle settling velocity is very less, let's say half the particle settling velocity, the one that is entering here will reach only half the height. But you can imagine whatever the particle entering at this particular moment, this part, half the particle, because this one travel only half, this travel h by 2, because the Vs is half of h over theta. That means it didn't go to the bottom, instead it goes only half the height. If that goes half the height, then you can imagine whatever the particle entering here will be escaping, whatever the particle entering here will be trapped. That means half of the particle will be trapped inside here, half of the particle here, this one will escape. So if I say, if I want to put the red color, this red color will go out, whereas this one, the black one, will enter to the bottom. That means your efficiency of removal now it's going to be half of what you could get from here, 100%. So you are going to have 50% removal. So therefore we can say easily neta, that removal efficiency is given by the particle settling velocity, which is Vs, divided by V naught times 100%. Here Vs was half, therefore you get half the efficiency. Here Vs was full of V naught, therefore you get 100% efficiency. Now the question comes, if Vs is less than or equal, those are the cases. In these cases we looked at Vs is less than or equal to V naught. Now if Vs is greater than V naught, what will happen? The situation here is Vs is greater than V naught. That means even before it reaches this one, the particle is going to drop down here. So if that is going to drop down here, that means all the particle will be removed. Still this is 100% removal. So this one is when Vs is less than V naught or less than or equal to V naught. But when Vs is more than V naught, you always get 100%. You cannot have 120% removal. You have to have a particle, and then that particle has to be removed. So therefore you can have only maximum 100%. You can't just apply this formula straight away. If I tell you Vs is, the particle is settling at I don't know, 2 millimeter per second, and then your overflow rate is 1 millimeter per second, then Vs over V naught times 100 is going to be 200%. You can't have 200% removal. You will have 100% removal. That's the maximum. I hope you understand what I wanted to tell you. So the essential point I wanted to discuss here, we can determine the removal efficiency in a sedimentation tank from a sedimentation velocity, which is Vs, of a particle settling velocity. This particle settling velocity, I think I didn't say Vs is particle settling velocity. I can say settling velocity. So if we know the particle settling velocity and overflow rate, we can determine the removal efficiency in a sedimentation tank. And then all I took effort so far is try to explain to you how Vs divided by V naught actually give you the removal efficiency, and then the removal efficiency can never be more than 100%. It is 100% is the maximum. That's the maximum all the time. Thank you.